Welcome to the Explainer. Today we're going to break down one of the most intuitive algorithms in all of machine learning, k-nearest neighbors. And we'll start with a really simple, familiar idea.
Okay, let's just dive right in with this saying. You've heard it a million times, right? Well, it perfectly captures the entire logic behind k-nearest neighbors, or KNN for short. The whole algorithm is really just built on this one core idea. You can figure out what something is just by looking at what it's closest to.
So how does a machine actually apply the duck test? Let's follow the journey of a brand new, unclassified piece of data and see how it finds its neighbors and, ultimately, its identity. The process is incredibly straightforward. I mean, it really just boils down to these three simple steps. First, it measures how far our new point is from every other point in the data. Second, it finds a specific number of the closest ones. Those are its neighbors. And finally, it just takes a vote to decide what our new point is. Let's see how that actually works. So first things first, we drop our new unknown point into a space that's already filled with labeled data. You can see the red circles are one thing and the blue squares are another. The very first thing KNN does is it calculates the distance from this new guy to every single other point on the chart.
Okay, next up, we have to decide how many neighbors we want to listen to. And this is the K. It's a really crucial decision. Do we ask just the single closest neighbor? Or maybe we should ask the 3 closest? Or 5? Or 10? Choosing this K value is a huge part of what shapes the final outcome.
All right, let's get to the final step and see how this all comes together in a decision. Once we've picked our K neighbors, it's officially time for them to cast their votes. And here it is, the final step in action. So let's say we decided that K is 5. The algorithm goes out, finds the 5 closest points to our new one, and then it holds a simple vote. If, say, 3 of those neighbors are blue squares and only 2 are red circles, well, majority rules. The new point gets classified as a blue square. It's really that simple. Now here's a smart little trick that data scientists use all the time. To avoid a deadlock, a tie in the vote, they almost always pick an odd number for K. Think about it. If you choose an even number like 4, you could easily end up with a 2-2 split between categories. But an odd number, like 3 or 5, guarantees you'll always have a clear winner. Now, when you apply this whole voting process across the entire space, you get a result that looks something like this. The algorithm basically carves up the space into a map of neighborhoods. The technical name for this is a Voronoi diagram, but all it really means is that any new point that happens to land inside one of these colored zones automatically gets assigned to the category of the point right at its center. But hang on a second. How exactly are we measuring what's closest? This brings us to a really critical detail. The idea of distance feels simple, right? But in data science, yeah, it can get a little complicated. Whoa, okay, I know this slide looks like a pop quiz from a math class, but don't worry, you do not need to memorize these formulas. The key thing to get here is that distance isn't just one single thing. There are lots of ways to measure it. You've got Euclidean, which is just a straight line, or Manhattan, which is more like moving around city blocks. The right one just depends on the kind of data you're working with. You know, the real problem isn't the formula. It's what happens when your features are on completely different scales. Just imagine trying to classify a patient using their weight in kilograms, which can be a big number, like 50 to 200, and also some tiny blood protein value. The huge numbers from the weight will totally dominate the distance calculation, and that tiny protein value might as well not even be there. This is exactly why standardizing your data is so important. So KNN is simple, it's powerful, but it definitely comes with a few major challenges that you absolutely have to be aware of before you decide to use it. So here are the main hurdles. We've already talked about picking the right K and the whole problem with different scales, but there are 2 other big ones. First, there's the curse of dimensionality. It's a fancy term, but it just means that as you add more and more features, like age, height, weight, location, and so on, all the data points get spread out so far apart that the idea of a close neighbor almost becomes meaningless. I mean, if you're in a gigantic empty room, is anything really close? And second, it's a resource hog. To classify just one new point, it has to measure its distance to every single point already in your data. With large data sets, that can be incredibly slow. And that leaves us with this final thought. Look, KNN's simplicity is its greatest strength, no doubt. It's so easy to understand, which makes it a fantastic starting point or a baseline model to check if a more complicated approach is even worth the effort. It really shines on smaller, cleaner data sets where its weaknesses don't show up as much. But as our data sets grow from thousands of points to millions or even billions, you have to ask, can this elegant, straightforward neighborhood watch really keep up in the age of big data?